Okay. Good morning, good evening to all around the world. A warm welcome and thanks for joining this webinar. I am Pradeep Sukumaran, Vice President Business Strategy at Ignitarum, and I'll be the moderator for this webinar. Before we start the session today, I would like to set a few ground rules. All the attendees will be put on mute, both mic and camera, throughout the session. For the questions from the attendees, we will use the chat option, which will be open throughout the session. So please key in your questions as they come. And at the end of the presentation, I will post them to the respective speakers and we'll try to cover as many as we can. So I'm hoping that we get a lot of questions from you folks. For a better viewing experience of the slides, I would recommend that all other tabs on your browser is closed. Also, would be good to close any other desktop or mobile apps that are heavy consumers of memory. This is to ensure that you get a clean view of the slides. There would be a few attendee polls that we would be throwing in during the session, also some handouts. So please do keep an eye out on that on your screen and request active participation. Okay, so let's get rolling. So today we gather here to learn from the industry experts on a very interesting application of video AI. We're going to look at how video-based deep learning solutions are helping improve maintenance of civil infrastructure. And by civil infrastructure, I mean railways, roads, pipeline, bridges, turbines, towers, like transmission, mobile, etc. Now, all of us have heard about smart infrastructure, and it's not a new thing. That's where IoT plays a big role. It's one of the main technologies. In fact, we can call it the foundation, right from the consumption to design to deployment and eventually maintenance. And we also know about predictive maintenance. We know of such deployments where sensors have been installed on various infrastructures, bridges, wind turbines, gas pipelines, railroads, and people are doing predictive maintenance, typically using TSP and in some cases machine learning algorithms. But more and more we are seeing deep learning being tried out to analyze these sensor data. Typically the sensors that are used include vibration, motion sensors, temperature, sound, etc. And in most cases, these sensors are intrusive, meaning they have to be installed on the infrastructure. And there is another class of sensors which is a very natural one for humans, which is vision. And you have vision sensors, which are artificial ones like cameras, which is fast becoming one of the key sensors for infrastructure inspection. And the best way to analyze video content is to use deep learning. And in some cases, a combination of traditional computer vision algorithms and deep learning. In today's session, we will see how vision analytics is being used for infrastructure maintenance and some new advancements in both software and hardware. Without further ado, let me get you all straight into this webinar with a brief introduction of our distinguished speakers. First off, we have Sujit Joseph, the Chief Product Officer of Ignitarum. In his role, he is responsible for transitioning technology components incubated in Ignitarum's R&D lab into commercially viable use cases. With a career spanning over 27 years, Sujit is a semiconductor industry veteran in the SoC system and the product architecture space. Prior to this, at SanDisk, India, he was the Director of Architecture in the Removable Products Group, which is a $2 billion business unit. Simultaneously, he was also heading the SanDisk India patenting function and drove academic research programs with premier Indian institutes. And prior to SanDisk, Sujit was the chief architect of the Semiconductor and Systems Unit at Wipro. Pleasure to introduce Barry Mullins, the Director of Technical Marketing from NVIDIA. He focuses on enabling customers in the Jetson ecosystem to bring deep learning and AI to the edge systems. For over 20 years, he has been engaged in developing, launching, and growing innovative and leading edge embedded products. He started his career as an embedded design engineer in Ireland and moved to San Jose in 2007 to extend his influence and impact in the technology space. Also pleased to introduce Bryan Wang from AVerMedia. Bryan is the BU manager of Middle East and India. With his prior project and sales management experience of over 14 years, he is in charge of project and channel business across the continent and has established strong relationship with government, public sector, and multinational companies. With this brief intro, I would like to hand it over to Barry from NVIDIA to start off with the first part of the presentation.
Hi, I'm Barry Mullins, Director of Technical Product Marketing for NVIDIA. And welcome to today's section of the presentation on inference and AI for edge and embedded systems using NVIDIA Jetson. Here you can see 2 data points from ABI research showing the rapid growth and adoption of AI at the edge. This is happening for many reasons, including the availability of higher performance processing to run AI, lower latency for AI and real-time analytics, the need to minimize data transfer and hosting costs, and for improved security. We are also seeing the growth of inference with huge momentum on Jetson. We now have over 500,000 active developers and over 3,000 unique customers actively deploying or developing systems with Jetson on board. This growth covers markets from delivery to manufacturing and retail to healthcare. Today with our partners AVerMedia and Ignitarum, we will focus on optical inspection, but prior to that, let me share some of the important considerations when designing edge AI systems and what NVIDIA provides you with. There are 2 aspects to AI. First is training, and the second is inference. Training is the development of the model, generally done in cloud-based systems or large server-based systems, using many of different frameworks to create the model. That DNN model shown in the middle here then needs to be optimized for inference, and inference is what takes place during the operation of a device or a product when it's actually applying the AI to the activities around it. When developing AI or models for the edge, it is critical that you bring these considerations into account. What types of models will you require in the system that you're designing? It may be dependent on many of the different sensors that you integrate into the product, but may also be dependent on multiple different models that will run in parallel or in series based on the data you capture. Also, the data you capture may vary in input size, whether you're capturing a wide scene and then want to do analysis on a very small piece of that scene, as in optical inspection maybe on a wafer in the semiconductor fabrication process, or if you're doing wide scene on a traffic intersection and then you want to pull out a certain vehicle or pedestrian or cyclists to count those people in the frame. There are many different frameworks that need to be accounted for, and systems need to be able to run those frameworks and optimize them for the edge. And there's also batch size depending on the number of streams that you have coming in or the number of frames that you want to or need to process together. And precision is absolutely critical because the different neural networks that you create may need different precisions at different levels in order to be able to give you the accuracy required for that application. It's important to keep those 5 ideas in mind, and there are 3 basic system requirements for any edge AI system. 1, it needs to be able to support diverse and complex neural networks. These neural networks are developing rapidly and are becoming ever more complex, and as you deploy a product today, you will need to be able to maintain and update those neural networks over time. So any system you choose must be able to run multiple ones in parallel and be able to run future complex networks. So it needs to be able to scale. There's also a requirement for the full stack acceleration. This means everything from the inputs and all of the sensor fusion that needs to be accelerated from a hardware perspective before you even get that data into the engines that can do inference, whether they're doing classification, detection, segmentation, and so on. And then once you have all that processed, you then need to be able to get it out, to be able to encode it, secure it, visualize it, and manage it in a very efficient, effective way. And you need to think about all of those pieces. Doing them individually can lead to different bottlenecks in the system, and it can also limit your system's capability for future growth or updated models as the system evolves. Lastly, you need to think about the whole deployment and management at scale. AI is not like a traditional embedded system. It is changing how embedded systems are built and how they operate. It is a learning system that continues to grow and evolve over time, and developers need to be able to update those algorithms independent of the base and foundational software in the system, but they also need to be able to update the base and foundational software over time and develop certain pieces of it and how it interacts with the AI or the systems or the environment that it's in. And then that needs to happen over the full life cycle of a product. And that cannot be done with systems being taken out of operation and into maintenance on a daily basis or a weekly basis or a monthly basis. That actually has to happen live over the air on a predefined set schedule, and that software has to be robust and integrated to make it very reliable. And many of those deployment and management scale also need to be able to be done in a secure, safe manner. And these are the requirements that have to be in all edge AI-based systems. Now, here you can see the Jetson family. It is made up of a system on modules. We do that because it's more efficient and effective for our customers to work with a module where we take on the design considerations of the complex PCB, the power supplies, and the memory, and we manage the life cycle of all of those components along with our own SoCs or system on chips. These modules are very efficient. They're small form factor, low power, yet very high performance that allow you to manage all of the inputs, the AI processing, and the outputs as described in the previous requirement for any one of these platforms. And because it's a module, we've abstracted a lot of the hardware from the software that we deliver, and this really enables us to give you a software-defined system because they all run the same software. You can run the software on any of these platforms, you compile it, and the performance will vary depending on the capabilities of the platform. And the key to it being a software-defined platform is what sits on top of that Jetson module, which is our Jetpack SDK. As you can see here, the Jetpack SDK includes a lot of CUDA-X software for deep learning, multimedia, accelerated compute and computer vision, and also a lot of sensor software that comes from many of our partners to be able to aggregate and do sensor fusion. We bundle all of that as a single developer kit. It comes on the Jetson, so you get it straight out of the downloads that we give you, and it's all open source where possible. We also give you a full suite of developer tools that allows you to optimize, analyze, debug, and get under the hood for that software to build it the way you want. Then we layer on top of that a couple of different vertical market SDKs, including DeepStream SDK, which I'll talk a little bit more about here today because that's what's used in the optical inspection and infrastructure side of things. And then we have our Isaac SDK, which is designed for robotics. So if you're into robotics, I'd highly recommend you go check out our Isaac pages in our Isaac SDK. And then this platform and this software-defined layer abstracts the hardware, which allows many different applications to be developed on top of that with various different software and sensors and services that come from our ecosystem or from many of our different customers and partners. If you remember, I mentioned that one of the requirements was deployment and management at scale from a software perspective for these edge AI-based systems. And our Jetson supports cloud-native capabilities that gives you the ability to deploy and manage software at scale. We support Docker Engine on the actual Jetson module. We run a full Ubuntu Linux system there that can be optimized for an embedded system based on the application. That can then run Docker on top of it. We have all of the libraries that are associated with the application you want to run and the CUDA acceleration libraries that can sit underneath that, and then you can put your container or your application specific software on top of that. And you may have a container for multiple different neural networks or different models so that they can run in parallel or together in series. And you can change those models over a period of time without changing layers of the underlying system. And this really allows you to architect a very scalable software system. It also allows you to create portability. If you have multiple different products with different underlying hardware systems, you can still maintain the same code base, compile it for those different products and deploy it to those different products. And the product will know when to pick up or which software to pick up based on how you define and optimize that software stack. Now, once you have that output model, and it'll come from one of these many different frameworks, it's critical that you optimize that model for inference at the edge. And what that means is that you optimize the model based on the underlying hardware and software stack that you're using. We have a tool called TensorRT that optimizes all modern frameworks and all of the complex DNNs that they create for the NVIDIA platforms. And it will do all of the larger scale server and plug-in GPU cards, but also all of our embedded systems. And we can use TensorRT to target that to our AGX Xavier or Nano or Xavier NX products. You just compile your code and it will use the CUDA acceleration libraries to then pick out the right engines on each of these modules to accelerate that model for you. And it takes a lot of the manual labor and the hard coding and the debugging required if you're manually doing this on a platform out of it, so that it's optimized for that whole flow. And being the leaders in AI, this is a tried and proven process across many different platforms that we have, and now we're bringing it to the edge, which is making it much more efficient to develop and deploy inference at the edge. Now, a critical piece of the AI deployment is also developing the model. And one of the things that NVIDIA has done is develop this toolkit called Transfer Learning Toolkit, which really optimizes that whole development process. It's much, much faster from a deep learning and training perspective because you start with a model that's already trained, and we give you multiple models that are trained. You just use your data on that model, run it through our transfer learning toolkit. It allows you to then optimize that model for your data and gives you a new model out at the other end that's ready to be used in multiple different systems and that. So if you're looking for a very fast way to deploy a model and get it up and running quickly, if you have a lot of data and you haven't got the time to develop your own model from ground up, this is a great way to go. You take a pre-trained model from us or from another source, you use your data, our toolkit will help you get there and get you an output model. And here I've included some examples of the pre-built train networks that we provide. You can use these out of the box. They're extremely accurate, and you can use them to retrain your data set to become your model for your application. There are 6 of them here. There are many more on our NVIDIA GPU cloud. And if you want to go and get them, you just go there, look for the ones you want and download them, and you're ready to go. Now this concludes my section of the presentation. I'm now going to hand you over to AVerMedia and Ignitarum, who are going to walk you through some infrastructure AI projects that they've done with Jetson and some of the experiences that they've had. So thank you for your time. If you have any questions, we'll take them at the end, or you can reach me offline at NVIDIA.
Thank you, Barry. As the NVIDIA Elite Partner, AVerMedia has served the role of ODM service provider to fulfill various needs of designing and manufacturing Jetson hardware solution. We've had over 30 years of experience in video capturing technology, which is predominantly known as frame grabbers. Since 2015, We've accomplished more than 100 projects with Jetson solutions to fulfill clients' applications like smart retail, smart factory, smart medical imagery analysis, and of course, the smart infrastructure inspection using airborne platform. The accumulated experience, along with the proven record of success, is due to the fact that AVerMedia was one of the earliest adopters of NVIDIA Jetson. During the past 5 years, we've observed exponential growth of demand on AI hardware, a lot of which comes from the Swift of x86 users who are seeking high-performance AI processing by smaller form factor and lower power consumption. Next, I would like to hand over the speech to Satish from Ignitarum.
Thanks, Bryan. I'm Sujit Joseph, Head of Products at Ignitarum. We are a 220-person strong company established in 2012 with engineering strength being equally split between software and hardware. We are headquartered in India with global offices in the US and Japan. Our business is primarily focused on providing AI and multimedia-driven solutions for a vast array of industries, leveraging deep understanding of the underlying hardware, especially GPU architecture. In today's session, we focus on infrastructure analytics as a core topic. Globally, infrastructure asset management is a constant challenge. It is labor intensive, requires specialized knowledge and equipment, and is very costly since it needs to be done repeatedly. Here are some interesting statistics. There are 2.5 million miles of energy carrying pipelines in the US alone. The oil and gas companies spend about $37 billion for asset inspection. If you look at the images on the left, these are some of the key infrastructure assets of interest. They include roads and rail tracks, pipelines and canals, power and cellular transmission towers, solar farms, wind turbines, buildings, bridges, tunnels. A fairly diverse set, as you can see, with the common denominator being that all of them are extremely expensive to maintain. In this session, the specific infrastructure asset we focus on is railroads. Here are some more related statistics. The so-called smart railways market is forecast to reach $39 billion by 2024. Within this forecast period, predictive maintenance is expected to grow at the highest CAGR. The US rail network has about 140,000 miles of track, so it's not surprising that the rail maintenance market in the US alone is very large, around $7.8 billion US dollars. The box on the left shows a sampling of the kind of checks that need to be done constantly around railroads. There are literally hundreds of these categories of checks. Some of them on track, some of them around track checks. On-track checks could be checking for things like rail warpage or errors in gauge or defects in plates. Around track checks, and these are shown on the extreme bottom right, could be checking for clearances or vegetation near the track or waterlogging or detecting whether there are drains which are clogged as they run beneath the rail tracks. Traditional inspection platforms range from a human inspector walking along the track, or you could have sensors mounted on a train engine, or you could have more specialized platforms as you see on the top right of the slide. You could have custom built inspection rail cars, which are very popular in Europe, or specialized on-track inspection trucks, which are used heavily in the US. Coming to the data acquisition systems, it could be as simple as a human using a measuring tape to check rail gauge, or using a hammer on a rail to listen to potentially telltale audio feedback. More automated systems include mounting RGB or perhaps even RGBD cameras or laser or X-ray scanners to the platforms that we talked about above. Terrestrial vehicular platforms are very good at data acquisition and have been over the years used to perform analytics of several of the on-track and around-track checks described earlier. However, they suffer from two key limitations. They are inherently intrusive, meaning the inspection vehicles need to work around critical freight or passenger corridor schedules. And secondly, the coverage area and hence the acquisition throughput are low. For example, a typical track-based inspection vehicle will cover 50 to 100 miles per day. Contrast this with the 400 to 500 miles per day that could be covered by an aircraft-based system. Considering the vast geographical spread of most railroad networks, this 10x or more improvement in coverage can result in significant cost savings. Also note that rail infrastructure maintenance is a very repetitive task, covering the same track area over and over again. So these cost savings quickly add up. Now we discuss the use of aerial platforms as against terrestrial platforms for infrastructure analytics. The aerial platforms of interest include fixed wing aircraft and drones, not the lightweight ones, but the heavy lift, high payload capacity UAVs. The panel on the left shows an actual use case where we use Ignitarum AI software to detect defects on power transmission towers using drones. Defects in this specific use case include structural anomalies like missing bolts, loose bolts, and girder warpage. In addition to anomaly detection, predictive maintenance correlated to other data points like storms and weather systems can enable more intelligent management of these types of infrastructure. The panel on the right shows another use case where anomalies on rail tracks are being detected. In the subsequent slides, we'll go into a lot more detail on this specific use case. The advantages of these aerial platforms are primarily wider coverage and their inherent non-intrusive nature during data acquisition. The track analytics workflow includes two parts, the image acquisition itself on the aircraft and detailed defect detection on the acquired footage. This happens on the ground usually. To avoid the intrusiveness that we talked about earlier, the aircraft would be flying at standoff distances, usually 1,000 to 1,500 feet away from the actual rail track. Long focal length lenses would be used to capture high resolution, normally 4K at 30 Hertz or 4K at 60 Hertz images. Note that we're capturing continuous video and not still images as part of this acquisition process. This is because the spatio-temporal nature of video can be nicely exploited for some complex use cases. After the aircraft lands, hopefully on its wheels and not on its nose, as the icon seems to be suggesting, the video footage would be transferred to ground-based compute systems for detailed analytics of the artifacts of interest. One of the problems with image acquisition from an aerial platform is the motion of the aircraft. As the aircraft pitches, yaws, and rolls, the region of interest, in this case the railway track itself, might not be fully visible in a frame. For fine anomaly detection, it is imperative that the track is clearly visible in every frame or at least most frames. We accomplish this by implementing a closed-loop AI-based dynamic ROI centering algorithm running on the NVIDIA Jetson TX2. This algorithm inspects each frame and then sends correction information to the gimbal on which the camera is mounted. As the loop stabilizes, the region of interest would be perfectly centered in each frame. Note that in real life, it won't just be a single track as you see in the images. There could be multiple tracks or complex crossings across the railway track. The algorithm can detect all of these and maintain dynamic centering. Note also that the ROI need not always be a railway track. We have implemented tracking and centering algorithms for roads and canals as well on the same Jetson TX2 platform. This slide shows the actual system that we deployed for the dynamic region of interest centering. The camera is mounted on a gimbal on the aircraft. The camera's HDMI output at 4K 30 is frame grabbed by the AVerMedia CN311 frame grabber card and sent to the Jetson TX2 based box PC. Note that the frame grabber card is actually within the chassis of the box PC and not outside as shown in this figure. Ignitarium's proprietary custom neural networks running on the TX2 inspects incoming frames, extracts contours of the rails via a combination of segmentation and custom classifiers, computes the centroid of the rails correlated with the centroid of each frame, and then generates correction signals. These signals would be sent via GPIO to the gimbal to adjust the camera position. A major benefit of this solution was that the pilot did not have to spend any manual effort on actually repositioning the camera during flight. The NVIDIA Jetson TX2 was chosen since it was able to run the image processing and the neural network workloads that were required for this application real time in a very small form factor. Jetpack 4.2.3 SDK with TensorRT and CUDNN libraries were used for development and neural network optimization. It's to be noted that for drone platforms, the Jetson Nano or the new Jetson Xavier NX would be really good choices. We chose the AVerMedia EX731 box PC since it packed everything we required for the application in a very low weight and volume form factor, from the HDMI frame grabber to the TX2 module to SSD storage to HDMI output for displaying the final results on screen. Now that usable video footage has been acquired using the dynamic recentering method that we described earlier, the aircraft lands and the data is transferred to the ground station. Note that with the low latencies and high bandwidth promised by 5G, this could very well be done from the air itself in the near future. For this specific deployment application, there were 3 rail track anomalies of interest, and you can see them on the right side. Cracked ties, that is cracks of various shapes and degrees on the wooden ties that stabilize the 2 metal rails. Skew ties, that is the wooden ties have been shifted in their position to an unacceptable angle. And 3, plate damage in the form of missing spikes on the plates attached to these ties. The image on the bottom right shows the post-detection and classification results on a single frame. As you can see, it's a fairly busy image where there are 30 odd ties, twice as many plates, and several hundred spikes per frame. The spikes are not exactly very clearly visible. To achieve this, complex image processing followed by multiple neural networks running in parallel are called for, requiring significantly higher compute requirements than the dynamic ROI centering use case that we talked about earlier. Since compute requirements were very high, but yet a cost-effective system was called for, we chose an NVIDIA Jetson Xavier AGX module enclosed within the rugged AVerMedia EA713 box PC. The compute horsepower offered by the 512 Volta GPU cores, along with the dedicated 64 tensor cores, was critical for running a host of neural network-based detectors, segmentation networks, and classifiers to be able to simultaneously process multiple complex anomalies, including very fine ones like missing spikes. Using the NVIDIA L4T, that is the Linux for Tegra board support package, we could operate in a familiar Linux environment, allowing a rich user interface to be presented to the user on the Xavier AGX itself. That is, without the need for an external host machine. In other words, a compact, completely standalone system that could do everything from ingestion of frames, running complex image processing and AI workloads, and also allowing UI-driven configuration and visualization was able to be deployed using the system. In the previous slides, we described anomaly detection using RGB cameras. However, these are just a small sampling of what is possible. Advanced analytics using multispectral or even hyperspectral camera payloads are in the works for detection of complex anomalies like chemical spills on track or gas leakage from freight containers. These are really complicated because the artifacts associated with these anomalies are often invisible. In summary, using the right choice of compute engines from the NVIDIA Jetson stable, be it the Nano, the Xavier NX, or the Xavier AGX, the right integrated box PC solution from AVerMedia, and purpose-built image processing and neural network algorithms from Ignitarum, it is possible to deploy practical solutions for addressing complex infrastructure analytics use cases from high-throughput aerial platforms. Thanks for listening in. At this point, I would like to hand over to Bryan from AVerMedia, who will talk more about their NVIDIA Jetson-based compute hardware.
Thank you, Sujith. Let's go over a little bit about the Jetson hardware offering by AVerMedia, which we call AVerAI. Jetson is oriented for deployments of AI at the edge. AVerMedia's design ideology adopts the spirit in provision of Jetson carrier boards of small form factors. We categorize AVerAI carrier boards in three sizes: Mini ITX, Pico ITX, and the smallest of all, the dimension of 87 by 50 mm, that is close to mobile ITX and is capable of being embedded into the most of the systems and turn those systems into Jetson-powered AI platforms. Dimension of the carrier boards tends to stay small under the entry and the mid-level spec, like Nano and Xavier NX, for the sake of cost saving, while they are being assigned to perform mission-centric operations that are simplistic and single-tasking. But size increases as the spec leverages to Xavier. Mini ITX boards are equipped with various mini PCIe, M.2 PCIe slots for expandability, where multitasking operations are made available with the same platform. In conjunction with video capture solution, the specialty of AVerAI box PCs comes with different options besides USB and IP cam signal intake. Our Nano and Xavier NX box PCs can host MIPI cam of 1080p or 4K resolution. AGX Xavier box PCs are capable of hosting multiple SDI signals, or even the combination of SDI, DVI, and composite inputs. Various signal inputs may apply to mission-critical operations, where multiple video sources are required into the same device simultaneously. For example, DVI and composite videos inputs are used for medical imaging analysis in the field of surgical operation. EX731AAN2 is chosen in this case for rail track inspection using aerial platform due to its capability of capturing the ultra-high resolution 4K P30 video that gets delivered flawlessly to Jetson GPU within 17 milliseconds only. The uncompressed 4K frames are the key to enhancing the efficient defect analysis that runs on Ignitarum's software platform. Imagine, when the airplane is flying at the speed of a couple of hundred miles per hour, how detrimental missing frames and low-resolution images can be on executing this operation. This is definitely not the concern with AVerAI solution. To ensure clarity of each and every captured rail track while the airplane is flying at high speed. We have all frame grabbers well integrated with Jetson by making sure that all frames are delivered stably, complying with the original image quality without frame drop. How do we do it? First, we integrate drivers of frame grabbers with Jetson BSP. Then, we take extensive length of time on stress test where burn-in is conducted 24 hours a day, 7 days a week. Once test fails, engineer team is engaged to take necessary approaches on justification. Then we run the 24/7 tests to be sure that this procedure passes quality assurance before the product is launched. This will come back and forth a few times due to the complication over sorting compatibility among camera, frame grabber, and the Jetson itself. Finally, we are then confident to guarantee the video processing quality on the total solution we offer with frame grabber and Jetson inside the box PC. There are a couple of key advantages over choosing AVerMedia. Besides the video capture technology that we've evolved for 30 years, we were able to design the size of the TX2 box PC, which is compact enough, say the size of Pico ITX carrier board, inside the box, which is very crucial in the airplane when the space is a real luxury. The power management system that AVerMedia designs on Jetson's solution can intelligently react towards the critical scenario. When confronting unstable power supply, every AI box PC will restart the system itself. And we also program auto start to those who demand instantaneous operation when the power source is connected. AVerMedia is flexible in terms of meeting demand on I/O customization. Besides USB, LAN, HDMI, and CAN bus, we help customize special I/O that are required from various verticals like aerial, medical, and factory automation. High degree of flexibility on customization concludes why AVerMedia was chosen for this project. Going forward, we're very happy to hear about your demand and like to offer our service to all of our B2B customers. Thank you.
Thanks, Barry, Sujit, and Bryan. Now we shall move to the Q&A session. We have a few questions that has come up. I shall go through some of them and direct it to the speakers. I hope you all enjoyed the presentation. Here's a question for Barry.
Yeah, sure.
Yeah, it would be good if we can get the speakers on video, please. Yeah, so Barry, the question is about the Jetson family. We know that the Jetson NX was recently launched, fills the gap between TX2 and the AGX, and pretty nicely in terms of performance and cost. Now, is there a plan to go the other way, which is to do a lower power version of the Nano, perhaps the Pico?
I think that's a great question. We're always looking at the different opportunities that are out there and the different areas of the market that are looking to adopt and apply AI. Right now, Nano is our lowest performance, small form factor, power efficient module. And that form factor we are keeping compatible with the NX that you just mentioned. And I would say, stay tuned over time. We've posted our roadmap slides up there, but we're always looking to adapt and change as the market requires. And that's so nothing I can talk about or bring up here, but we're always looking into what's available or what's required by our customers.
Yep. Thanks, Barry. Here's a question for Sujit. Isn't it more appropriate to do the actual anomaly detection in the cloud or on a server class GPU farm?
Yeah, good question. In fact, yes, that is the typical conventional wisdom to do the the heavy lifting on a server class instance, either on the cloud or in premise. Now, if you look at this particular application that we talked about, there were three specific anomalies of interest. Also, the solution had to be implemented within a particular kind of cost envelope. And since the AGX had fairly serious amount of compute horsepower, even though the traditional method would have been to do this in premise on a server class or on a cloud, we were able to do this on the AGX. I mean, remember that it's a fairly powerful machine in such a small form factor. So yes, if the number of anomalies that had to be processed were much more, and the throughput of result generation had to be higher than what it was in this case, yes, we would have gone for a server class. And incidentally, we've got the same algorithm running on a NVIDIA Titan XP class GPU as well.
We see a lot of our customers that look for real time or as close to real time inference as possible, where they may not be able to get back to a cloud or wait for that data to go back up and come back down, particularly for some of the drone inspection applications that are being used on, we have some that are being used on wind turbines to inspect the blades, or oil and gas pipelines. What they want to be able to do is quickly get a result so that they can dispatch crews or repair anything that needs to be repaired immediately, not have to wait for offline tasks and then schedule things that happen later. And with the array of products and the software that this team has brought together, you can see how you're reducing that time where you could do a short number of miles and for inspection, you're able to increase the overall number of miles, and then add to that the ability to be able to put crews where they need to be quickly. Makes it safer for many of the railway companies and any passengers and so on that are on there. So the quality of service and the kind of reliability they're able to offer is much, much better by having that real time or at the edge. And you'll see that a lot of the software we put in place is designed to enable what I would call server class capabilities in these small, low power, small form factor, rugged boxes that AVerMedia provide.
That is good. I guess this question is again for Sujit. The question is, will such a solution include the drone with the camera or the camera on top of the train? And does the solution include capturing the images and detecting anomalies in the railway infrastructure case?
The solution provided by Ignitarum is only the software part. We, of course, rely on partners like AVerMedia to provide the compute infrastructure. And we tend to use third-party sensors. I mean, typically COTS sensors, whether they be an RGB or RGBD. So the sensors would come from third parties. Similarly, the drone platforms also would come from third parties. The solution provided by us would only be the software. And of course, the integration, all of these to achieve the specific solution to be deployed.
Question for Bryan. Even though the box solutions from AVerMedia provides protection from the environment, for industrial applications, there is a need for industrial modules. And since we are transitioning from TX1, TX2 to NX modules, can we expect an industrial version for them? Bryan? The question is about the industrial versions of the AVerMedia box PCs.
Hello, thank you very much, Pradeep. Actually, what AVerMedia does is that we are, our profession is basically providing the audience service to all the required specifications. So I would say yes to this question on the creating
industrial version or the ruggedized version of the box PC on the all kind of Jetson solution that we offer. So there, as the requirements is on the ODM basis, I think to fulfill the various demands with the specific customizations, that will be possible, yes. As long as you bring us your requirements, we will be able to fulfill them.
Yeah, Brian. I think this question.
I'll jump in here as well because I think it's very relevant to what we have done for our robot. We have a TX2i, which is an industrial qualified TX2 part. So you get all of that capability in that module that is ruggedized. That is every component on the module we deliver is qualified to an industrial level. And then AVerMedia, they take that and they box it up and they make the rest of the components and the interfaces in the box ruggedized as well to meet the same industrial specifications. And next year we will have an AGX Xavier industrial module that will come out, and you'll be able to use that module for us. Or if you, like Brian explained, if you wanted a custom built ODM box, they would work with you to make sure that the requirements that you needed were met and that they were able to put it all together in a ruggedized format using an industrial module inside in the system. We are not planning to do an NX industrial module right now. But what AVerMedia and that can do is they can take that, which has got a pretty high spec from a temperature perspective and so on, and build it into a module or into a box where that box meets the ruggedized requirements, even though some of the components like the module inside it may not be full industrial spec from a temperature perspective and so on. So there's a lot of capabilities that AVerMedia brings to the table that builds on top of the modules that we provide to make sure that the system of the box is done that way. And then of course, you know, you put the software on top of that to be able to do all the AI and management, and that's where Ignitarum has their kind of expertise.
Related question. I just realized that the question is any comments on the multimodal kind of system which may prove to be much better. Here's a question for Barry again. All the pre-trained networks mentioned in your slides are for video and image-centric workloads. So does this mean it represents a sweet spot target for the Jetson family, or are there other ML workloads like audio, vibration, other sensors that could be a focus area for the Jetson platform?
Yeah, that's a great question. I think video is one of the sweet spots for sure. It is definitely low-hanging fruit in terms of Jetson, because we have built MIPI interfaces, we have USB interfaces, and Ethernet interfaces that are able to bring in all of those video streams. But that said, if you look at one of our recent demos from the last GTC, we have shown that we're running BERT, which is a speech recognition, and running that completely on an NX system where you can actually have conversational AI running. So there is audio and that has been run and some applications there. But you can apply this to any AI application for any data set, whether it's you know, vibrations or other data, mathematical models that you want to run, because what you're able to do is take in the data through many different interfaces, and then you're able to tap into the power of the GPU or the deep learning accelerators and the other blocks that are in there. And then, of course, you can get that data back out through many different interfaces, including, because we run a full Linux desktop, you can bring it out to a display there locally and have great resolution for, you know, immediate analytics and visualization.
Yeah, in fact, that is something that is happening even as we speak. Adding on to what Barry said, while video might be the most logical data for analytics in this kind of use cases, as we said earlier, you can augment that with other sensor data like vibration and audio. If you remember, we had talked about using, say, a hammer on a rail to figure out whether the rail is okay or not. Now, there are things like smart hammers being built, where analytics could be done using the audio signatures that are coming from the sheer sound of the system, knocking on a rail, for example. So yeah, it's a very good point. Multimodal systems where audio, video, vibrational data all being fused together. These are all happening, and these can very efficiently be done on the Jetson stable.
Yeah, and we see that in different applications in different areas, particularly when we look at some of the robotics side of things, where they actually do use multiple different sensors, including things like LiDAR and
one more question.
audio
This is
to interact with the environment around
okay,
it.
yeah,
And you can
so we're
apply that
detecting the anomaly on the
in
track,
any of
but
the different
how would we
scenarios,
correlate
including
that to the actual location on the
inspection
track?
and infrastructure and things like that.
A question for Bryan. Does the box PC portfolio support PoE, power over Ethernet?
We are following on the NVIDIA's path on creating the PoE solution and on the Nano and the Xavier NX solution. So talking about the model numbers, it will be realized on our the EN715, which is the Nano, as well as the NX211B, which is on the Xavier NX model.
This, I think, is a question for Sujit. The question is, what is the wireless communication between Jetson and camera?
There is no wireless communication in this example. The camera is physically wired over HDMI to the HDMI input port of the CN311 frame grabber card from AVerMedia. So there is no wireless communication. And also note that this system is working in a relatively hostile environment. That is, it is inside the aircraft. So typically, wherever possible, we would tend to do a wired system if we can get away with it. So there is no wireless connection between the camera and the Jetson in this example. This is it's a bit of a complicated problem, but fortunately it is a solved problem. So typically what is done is the aircraft anyway has its own position. It knows where it is. And its AGL and angle of attack with respect to where the track is correlated using the field of view of the camera. And there is a bit of math involved in this. Using that, you can correlate the location of the anomaly with respect to its position, on Earth. So it's slightly complicated, but it's a solved problem.
I think, let me just check if I'm missing out any of the questions. Yeah, I think there's one which I, so for Sujit, so what kind of RGB cameras are you using, and do you process all the frames, and what's the FPS?
So again, these are, if you talk about this specific use case that we talked about dynamic centering followed by anomaly detection. As I said earlier, we're using, it's not a custom camera, it is just a COTS camera from the usual suspects, the Panasonics and the Nikons of this world. One difference is that the focal length is pretty high. It is 1000 plus millimeter because the aircraft is flying so far away. So it's in this example, it's a regular RGB camera, just that the focal length is quite high, and the resolution is quite high as well. It is 4K 30 Hertz. Of course, there are other use cases for anomaly detection where depth sensing cameras and lasers and X-rays are being used heavily as well.
we are done with the questions, and we also are just about, yeah, we just covered the full 1 hour that we planned for. So if there are any more questions from the audience, we could wait for a few seconds more. Okay, I think that would be it from the audience side. So thank you so much, Barry, Bryan, and Sujit, and thanks to the audience and the attendees also.
Yeah, thank you to everybody who attended, and hope everybody stays well.
Yep. Thanks all. Have a
Thanks,
good day, good evening. Bye.
Bye.